My name is Bob Newton. I'm a professor emeritus at Smith College. Um, and I have mapped the Ossipee Lake quadrangle, 15-minute quadrangle for the surficial geology for the state of New Hampshire back in the early 1970s. I'm also a member of the Barnes Aquifer Protection Advisory Committee for over 20 years. And what that committee does is it provides comments to planning boards on developments in the area of the Barnes Aquifer, which is another large aquifer in Western Massachusetts, similar geologic setting to the Ossipee Aquifer. So what I want to talk about today is why the Meena site is particularly bad location for a gas station. And so let's get started. Okay, so the first question is, what is an aquifer? An aquifer is simply any geologic material from which usable quantities of waters can be extracted. So it has a very general, easy definition. If you can get water out of it, then it is an aquifer. And so with that definition, we can think about the Ossipee Aquifer. The Ossipee Aquifer was studied by the U.S. Geological Survey in 1995, with a report in 1995 by Rich Moore and Laura Medali. And they identified this aquifer as one of the largest stratified drift aquifers in New Hampshire. So it's a large aquifer, as you can see on the map here. The blue areas, the darker blue areas, are more high-yielding parts of the aquifer. It runs roughly from Silver Lake through Ossipee Lake and down the Ossipee River. The site, the Meena site, would be located about where the cursor is right now. You can see in one of the darker blue areas. So this is the aquifer. And I want to talk a little bit about how aquifers work. So this is a cross-sectional view of a simple stratified drift kind of aquifer, meaning that it is made up of simply sand and gravel deposits. And you can see here that what wells put into it would define a water table situation where you hit the saturated zone shown in blue, unsaturated zone up here in brown. So this is an area where, when it rains in this area up here, the water infiltrates into the ground and comes down, goes into the saturated zone, adding water to the aquifer, and then that water is moving into areas of discharge. So the groundwater system is a dynamic system with water entering and exiting through the system. And it's entering through these recharge areas, which are relatively high, where the permeable materials are exposed at the surface, and it's discharging into the surface water systems, so either rivers or lakes. So there's an intimate association between groundwater and surface water. So this is sort of a simplified version, but we're going to come back and look at this a little bit as we consider the Meena site and where it fits into this picture. This is a view of the part of the Ossipee Lake 15-minute quadrangle that I mapped back in the early 70s. And the different colors here represent different kinds of stratified drift deposits. And by stratified drift, what we really mean are stream deposits of sand and gravel from meltwater streams associated with the melting of the continental ice. So all the different colors, except the green, are stratified drift deposits. And one of the things I want to emphasize is that there's a lot of different kinds of deposits. So on this map, the different colors represent different depositional environments with different kinds of sediments. And so they'll all react differently in the groundwater system, but they're all part of one groundwater system as displayed here. And of course, the the Meena site is down here where the cursor is at the edge of this sort of bright reddish colored area. So surficial materials are the aquifer that we're talking about today. All right, so let's look at some examples of these deposits and how they form. So quick little trip to Alaska. This is the Herbert Glacier that comes out of the Juneau ice field. And you're seeing the ice, and then you can see sort of in the foreground here a meltwater stream. And if you can look carefully, you'll see a couple of people here for scale. And you see these huge deposits of gravel. And this is just turning and looking downstream. And you see the rivers here are depositing and completely filling up the bottom of the valley with these coarse sand and gravel deposits. And as you look further downstream, so going back to this one, if you were to walk downstream, you'd see it would change from gravels to sands to finer sands as you move downstream. So now let's turn and look at some of the deposits that make up the Ossipee Aquifer. So these are all local slides of the Ossipee Aquifer. And here we see a typical exposure in a gravel pit of meltwater stream deposits. They have a range of materials from coarse gravels to finer sands. But this is, in fact, the aquifer. And this is the unsaturated zone of the aquifer, and beneath our feet, looking down below, we would go into the saturated zone. And this is a primary recharge area to the aquifer. You can see the gravels are exposed right up to the surface. And so when it rains, water will infiltrate through these very highly permeable sediments. Another view of a slightly different pit. We can see it's a little bit finer grain, has these wonderful sedimentary structures which tell us a story about how groundwater is moving through this system. And I don't have time to talk about that story, but it's really interesting. And another place further downstream where you're seeing it's getting more fine grained, but a flat surface. This is the Pine Barrens in Tamworth, Madison, Freedom area. If you look carefully, you'd see Mount Chicago is right there. But this is the heart of the aquifer, and you can see these sands, very permeable materials. And if you were to go to some other places, you might find these very fine grained materials associated with glacial lakes. And these are referred to as barved clays. And they're interesting because they're annual deposits with a winter clay layer, a summer silty sand layer. And these, of course, you would not get as much recharge or groundwater moving through these deposits because they have a lot of clay that sort of blocks the flow of groundwater. And then all the other areas on the map that weren't those bright colors, the green areas on that map, are the deposits that were formed directly from the glacier. And they can be of secondary importance, but these are the glacial tills, typically unstratified, bouldery. In many examples like this is sort of a typical exposure in glacial till. And then we have two tills in the local area. The other till is a much more dense, hard material that we see here. So tills are not going to make good aquifers, but the stratified drift will. And so here is the topographic map with the aquifer marked on it. And the point here is that, well, this is the aquifer, but now we know that different parts of this aquifer are going to have different characteristics based on the type of geomorphic features that are present on how they were deposited. Now let's look more carefully at the Meena site. So here is the aquifer, Levitt Bay. Here's the Meena site. Here's the town line between Ossipee and Effingham. And here's the aquifer protection zone that Effingham has and the one Ossipee has. And you can see that all the areas of the aquifer have been protected equally, and as they should be. But we know that some areas need to be protected more than others. So again, here's a blow up of the aquifer, just looking at the Effingham side, and here's the site. And on this topographic map, which is the 7.5-minute map, we can see a little bit more in the topography. And if we were to superimpose the geologic or the surficial geologic map on top of it, it would look something like this, where we have different materials in different areas. It's not homogeneous. And this orange area would be the area that is made up of what's in this case is what's called a cane delta, but it's a pile of sand and gravel that was deposited by a meltwater stream where it entered a lake. And in fact, this is over here, the yellow is the beach associated with the lake. And then these flatter areas are going to have deposits. The surface is going to be covered with deposits from that lake. So they're very different kinds of materials between here, here, and here. The blue represents swamp deposits that are right at the surface. The purple is going to be more of the finer grained deposits associated with the lake. And this is the coarsest material here. And it fits a story of how the glacier retreated from the area. And at one time, the ice front was located here. And south of the ice, there was a lake shown in blue here. And then there were deltas built into the lake by the meltwater streams. And this is just a cartoon showing a couple of those deltas. As we will see, there's another delta right here, a large one here, some outwash here, and a wonderful meltwater channel that drained the lake here on the north side of Green Mountain. So we have to look at the site in terms of how it fits into this sequence of deglaciation and the nature of deposits in different areas. Okay, so I'm going to take a moment here and talk about a new technology that's going to help us understand what's happening at the site. And I guess it's not that new. We'll be looking at this airborne laser scanning using this light detection and ranging system, or LIDAR system. The LIDAR was first developed by Hughes in 1960, and the airborne ability to use it was really developed in much more recent times, when we had better computers, better global positioning systems, and we can use this laser, and essentially think of it as a laser that you're shooting out of the airplane to the ground, and you're timing how long it takes for the light to go to the ground and bounce back. If you know exactly where the airplane is, then you can know exactly where the ground is and what the elevation of the ground is, if you know the elevation of the airplane. And so that's what LIDAR does. It gives us very accurate elevations. And it does it using millions of points. It takes tremendous amounts of data. So in this little area that's about a square mile, you're collecting millions of points, and you're getting elevations of everything that light bounces off of. So the tops of trees, the middle of the trees, and then in areas you get through the trees and you see the ground. So this is called the point cloud. And from this point cloud, you can separate out the ground and just look at that area, the elevation of the ground surface. And you can get a very detailed map of the surface. And the LIDAR data that's collected for New Hampshire, available for New Hampshire, is collected such that there's an elevation every 2.5 feet on the surface of the ground. So you think about that, that's a lot of points. Now, actually, there's many more points than that were collected. And then that data was then used to create a raster that has points that are 2.5 feet apart. So think of it as a grid with elevations every 2.5 feet. And you can use that grid to create a digital elevation model. And so that's what we're going to do, is we're going to use digital elevation models to look at the surface of the Earth to get a better view of the geomorphic features that are there and how what that tells us about the materials that are there. So here is a LiDAR-based digital elevation model that uses the sun, puts the sun in the northwest corner of the landscape at a height of 45 degrees above the horizon. And then you illuminate the model with the sun, and you get bright and dark areas based on whether a slope is facing the sun or is in shadow. And so that gives us this view. And we can see features in the landscape that we've never been able to see before using this technology. So we're going to look at that and sort of use that to understand the features that occur in this area. And we can see this Kame Delta here that was formed when the ice stood here. We'll just put a line here. So here's the ice up in this area. Here's the lake over here. And these are the deposits that were created by the streams as they poured into the lake and carried sediment. And that sediment was deposited by the meltwater streams right at the ice front. And there are even these ridges, which are probably eskers that run into the delta. And that tells us where coarser material is likely to be. And the first thing we'll do as we look at this is to look at the Meena site. Here it is. And we can clearly see that this site has been disturbed. In fact, it's an old gravel pit. And here's the working face of the gravel pit. And here's the flat surface where everything has been removed. And this is where the Meena site is located. If we look at air photos, here's 2006 air photo. It's an ortho photo, so the parallax has been removed. And we can see the old working face showing right along here, where the sands and gravels are exposed. And then if we look more recently, the last one is in 2015, we still see the working face of the front of the gravel pit. So this site is an old gravel pit. And why is that important? Well, it's a place where the coarsest materials were exposed and mined. And so all that unsaturated zone has been removed. And although materials move through, water moves through it very easily, there is the potential for some attenuation of contaminants as they move through the unsaturated zone before they get to the saturated zone. And so all that's been removed. And we've left with the most permeable materials exposed at the surface with not a thickness to protect it to the water table. So this is the worst possible scenario, to be actually locating a gas station in an old gravel pit. Let's look at a topographic profile. So this red line represents a line where we're going to look at a cross section of the topography. This, we can clearly see Route 25 running this way. We have the site. We have old Route 25 coming here. We have this high area here. We have perhaps an esker feeding right into the heart of this site. And we have a bunch of kettle holes over here where we were right up in the ice when this deposit was formed. So I'm going to look at a topographic profile along this line, because remember, the LiDAR gives us elevations every 2.5 feet. So if we do that, we can see this is the profile. Elevation, and this is elevation above sea level, and distance in feet. So elevation in feet, distance in feet from where the profile started. Again, this would be Route 25. Here's the site. We can clearly see the notch that's been taken out of the landscape by the mining. Probably the old landscape maybe extended something like this. And then this is the feature that is the most coarse material that was formed at the margin of the ice. And then this is later material that was deposited out here. And out here is Levitt Bay. So let's add to this profile the types of materials that are in this area. So it's the exact same profile, but we've added symbols for the different materials. So this feature is going to be a Kame Delta complex with maybe eskers associated with it, and it's going to be made up of the most coarse material. Once we go in the aquifer to the south, we're going to get into finer grain material that's essentially lake segments. And once we go to the north, we're going to get into older material or that was deposited, or actually it's later material that was deposited out here into Levitt Bay. So this deposit right here, which represents the primary recharge area to the aquifer. Groundwater enters through this system, and it's flowing out in all directions from that area here. Route 25 is on this little ridge that was artificially produced to raise the road above the wetlands along Phillips Brook that lie on this side. Here is the site of the gas station. There's a public water supply well right here, right next to or part of the gas station. There are lots of private wells in the area here at Blueberry Estates, and many wells out in this area. And many of them are just driven points that drive down into this aquifer where the water's coming through this area. The primary source of water is coming through this primary recharge area. This depression right here was created when Route 25 was constructed. So this is, as we'll see in a moment, this is the infiltration basin. So here is the area, here's the gas station here. And I just put this aerial photograph in here, and I have the property boundaries just to give you an idea of how many houses, lots are available for building and how many people have already built out here. All of these wells, all of these properties are supplied by private wells. So there's a well associated with almost every one of these squares, and it's primarily being recharged from the area where the gas station is. All right, so let's talk briefly about stormwater. Stormwater is a big issue with gas stations, not because it's going to increase the flow of rivers, but because the water that washes off the surface of the gas station carries with it all the contaminants that are left when gasoline is spilled. So this air photo, we've taken and added contour lines using the LiDAR. So these are LiDAR-based contours, and you can see the ridge that Route 25 is on, the flat surface of the area of the gas station. And then the plan is to run all of the stormwater runoff into this infiltration basin, because this closed basin here, this hole in the ground, is so incredibly permeable that all the water infiltrates. And there's not even any exit pipe out on this side. It's all infiltrated. Any water that runs off the impermeable surfaces of the gas station will infiltrate into the groundwater directly. So if there are spills or anything else that happens here, it's going to go directly into the groundwater. And the amount of surface runoff we can calculate on an annual basis based on the area of impermeable surfaces and the amount of rainfall. And so we're talking about over 800,000 gallons per year is going to be infiltrated into this basin. Looking more carefully at the basin, we can see some evidence right here that occasionally the water level, the water table comes up into the bottom of the basin, and we can sort of examine this by looking at the topographic cross section across here. So we go E to F here, and you can clearly see the depression in the landscape. And if we look at the topography, it looks like this. And here's the gas station up here. And then here is the floor of the infiltration basin. Here's that place where we see that evidence for ponding. And I guess it's not much of a surprise because over here is Phillips Brook. This is the artificial fill for making Route 25. And Phillips Brook is probably close to or at the water table. It's a point of discharge of groundwater. And so, it's at an elevation of about 413 feet. The bottom of the floor of the infiltration basins at 415 feet. So there's only 2 feet between the two. So it's not surprising that occasionally, maybe in the spring or during high rain events, that the water table rises up into the bottom of the infiltration basin. But even so, all the water that accumulates here ends up in the groundwater. And that is the problem, especially when you consider the possibility for spills at a gas station. Spills at gas stations are extremely common. And I have this sort of background to this slide. You can see this gas pump, and you can see all this. This is actually gasoline in the background here that's coming out along the surface. And this is an event occurred just a few weeks ago in California, December 20th. And a SUV backed into, and it didn't hit it very hard, it's all on security camera, backed into the pumps, and the resulting spill was 1,300 gallons. If that were to happen in this case, 1,300 gallons of gasoline would go into the aquifer and would recharge the aquifer. You don't want gasoline in your aquifer. Now, how often do things like this happen? They happen fairly frequently. So I went through the records for Carroll County from DES, and I just took examples of the kinds of things that happen at gas stations that cause gas spills. So Molten Borough, 20 gallons, drive off with a gas hose attached. So someone was filling their gas tank, and then they forgot to take the hose out, and they drove away. Now, there are safety devices on the tanks that are supposed, on the hoses that are supposed to cut off any flow. But in this case, 20 gallons spilled before that actually happened. North Conway, 20 gallons spilled when the car's gas tank, they filled the tank and then the tank failed and leaked all over the parking area associated with the gas station. So that's another way you can have a spill. Bartlett, 45 gallons were spilled when the snowplow hit the pump. Well, that was Bartlett's. That's not too bad. 45 is nothing compared to SUV hitting the pump with 1,300 gallons. Now, these all have safety features associated with them, but and California's safety procedures are much higher than most states, and still their safety devices failed in this case. 1,300 gallons. Wakefield, that we all do this. We set the gas handle so that it fills. We don't have to hold on to it. Well, in this case, the fill shutoff failed. There are many examples of this. 25 gallons was spilled. Again, there's supposed to be some fail-safe device, but it doesn't always work. Ossipee, 30 gallons. This is very common that when you fill your tanks, the big tanker truck comes in and fills the underground storage tank. Sometimes there are problems and spills occur. In this case, 30 gallons was spilled. And in Wolfboro, there were 20 gallons spilled when the gas pump leaked. That's exactly this kind of scenario. So these things happen. If they happen at this site, they will contaminate the groundwater and will directly contaminate the wells in the area. It's for sure to happen. There's a lot of information out available about this if you want to learn more about it. There's EPA's put out a number of documents. These are just a couple examples: preventing leaks and spills at service stations. What do you do? So here's a document. This is a fairly old document. There's a much newer one, this one from 2020, and it's current best practices in maintaining hydraulic control at fueling facilities. And this hydraulic control, they're talking about runoff. And what do you do to prevent runoff of spilled material from the gas tanks, from the filling operations? And so there's a lot of information on the kinds of infrastructure that you can put in to help control this. But in no cases can you be 100% sure. And with a location like this, where you're located in a gravel pit, it's just not gonna, it's not the place to be doing this. And finally, New Hampshire, the DES has put out their own document, an environmental fact sheet on how municipalities can protect their groundwater supplies and what they can do. And this was just put out in 2020. And so it's fairly recent, and it takes into consideration all the new technology that's out there. But even with that, they say, given the likelihood that UST systems release gasoline constituents, most commonly in the form of vapor leaks from underground piping systems or overfills of the UST, as we've seen examples in Carroll County, vehicle tank or portable containers overflows, yes, we've seen examples of that, and the possibility that spilled fuel would be carried off the fueling area by stormwater. Municipal officials interested in providing the highest possible level of protection for groundwater used for drinking water should consider restricting the siting of gas stations as they would for any other land use that is likely to contaminate groundwater. If the municipality's zoning ordinance prohibits the location of certain high-risk land uses in wellhead protection areas, aquifer protection areas, or other areas of high value groundwater, gas stations should be considered for inclusion in the list of prohibited land uses. Of course, Effingham has already done this, but here we are. It's been overridden. And so the question is, what do we do in this case? This is the worst possible place to put a gas station. In all of the aquifer protection zones, this is the worst possible place, an old gravel pit. It's unconscionable to do. So I'll end there and answer any questions.
Hi, Bob. I have a question for you.
Yes.
I'm just wondering, I know that these groundwater protection ordinances were put in place as a preventative measure, so that towns down the road wouldn't have to necessarily deal with expensive cleanups or impossible cleanups of pollutants getting into their drinking water. Do you have any experience with a cleanup? And is it possible to clean something like that up once it's in the ground? How expensive is it? And really, what would folks be dealing with who own wells downstream of this gas station should there be a contamination event?
Yes, so there are ways to mitigate the spill. If there was a large spill in this location, then what they would try to do is to pump it out, and you pump the groundwater and you create all this wastewater you'd have to get rid of. So one of the things you could do is to pump put a large groundwater well in and start pumping like crazy, and to try to capture all of the spill. You would not be able to do that. You wouldn't be able to get it all, but you might be able to get some. So you could do that kind of technology. You could actually do some bioremediation where you might pump air into the system and try to get microbes to break the gasoline down. But in this situation, this is an unusual situation because you're in such permeable materials that it's unlikely that you'd capture everything. And there would have to, the solution would be to put in an alternative water supply for the people in the area. Ultimately, that's what would have to be done. You would not be successful in treating the water, nor would it be possible really to treat water at the source. You know, where you at your own well, you couldn't put in it would be unlikely that you could put in a system in your house that would be able to treat it as well. As if you did, it would be extremely expensive because it'd be a activated charcoal system. So I think that while there are some technologies that you could try to do it, ultimately you would have to put in alternate water. And who's responsible? Well, the courts will have to decide who's responsible because someone will be suing someone else for sure. So I can't say who would be paying for it, but it would be extremely expensive because ultimately it would involve putting in an alternate water supply. Blair.
On that note, can you go back to those two slides that showed, one was the recharge area that showed the two wells at Blueberry Estates, and the other slide showed all the tax maps overlaid. It also showed the town line of Ossipee and Effingham. And to what Tara just asked, the one slide only showed two wells going down into the aquifer because it was just a slide. But the overlay slide that showed all that tax map, there are so many houses there, yet they're all in Ossipee. And so my concern is the spill happens in Effingham, or who's walking away from this? And who's responsible to pay for this?
So,
and should the planning board deny this permit based on the amount of people it's going to impact?
okay, so let's try to go to each one of those. So the first one, this diagram right here is the one I think we meant, and it shows some wells. Now, this starred well is a public water supply well, which is essentially right next. It's on the site, essentially. And this is the other wells, like this one. This is where Blueberry Estates is, and so there are a whole series of wells here. It's not just one. And there's a whole series of wells here. So I just put a couple wells as representative to the large number of wells that this is what you're referring to here. So we're located here. That municipal well is located here. Blueberry Estates is up here. And we can see that there are lots of properties all around here, which will all have wells, and all these will have wells. And the town line is right along here. So in fact, by far, most of the people who are impacted will be, the vast majority will be in Ossipee. So, you know, that's it's clearly a problem mainly for the people in Ossipee. Still, this gas station.
Thank you.
I'm not sure I answered the question, but
thank you.
Can I tag team with that a little bit? Since most of these people are on private wells, how would they even know if there were contaminants in their water? In New Hampshire, the responsibility is placed on the individual homeowner, and there's no, mandatory testing required by the state. So I'm just wondering, how would they even know if their water was contaminated in the first place? And even that public well that you showed in the previous slide, as far as I know, they don't have to test for VOCs, which would be the only way to detect some of these contaminants, the ones that cause cancer and more serious health effects. And then for an individual to test for VOCs, it's really cost prohibitive. I think it costs like $250 to just do one test. So in your experience and your knowledge, you know, if a contamination event happens or there's contaminants in somebody's well water, how would we even know?
Yeah, so that's, I think you've hit the most critical issue here. And that is, we wouldn't know until people started getting sick. And if of course it was a big spill, if it was 1,300 gallons, well, we'd know, everybody would know. But there's a lot of recent research, which I didn't talk about, that says that just normal gas filling operations, there's always a little bit of spill that happens. It's very frequent, and drops of gasoline are, with every fill up, are coming out of the end of the pipe and hitting the ground. And if you go to a gas station and look at the ground, you will see that there's a lot of staining on the concrete from just small little spills. And research is showing that those little spills are enough to contaminate the groundwater in certain situations. And this would be one of those situations because it is so permeable. So in that scenario, there would be no way, because as you have correctly pointed out, even the public water supply well at that site is not tested for VOCs. And the only way you would know is to test for VOCs. So in my experience in these situations, we always push to have municipal water supplies provided to these areas that are so susceptible to contamination. So if a gas station were in that location, we would be trying to get a town water line into those properties so that they would go from having their own well to being on town water. I know there's no town water in Effingham or Ossipee in this area anyway, but that's what that's what you'd have to advocate for, because in those larger municipal water systems, the water is tested on a regular basis for VOCs. And so you would know that those people would be drinking pure water. So if you put a gas station here, ultimately you should be putting in municipal water to protect those people, because it's such a sensitive site. So yeah, and of course we all know the cost of doing that is tremendous. It's prohibitive for most towns without having some federal programs that help provide funds. And there are some out there, but I mean, that's what you're talking about. You're talking about putting in a lot of infrastructure, and